Hi everyone. Today we're going to be talking about our computational pipeline that we've developed to assess menstrual cycle influence on continuous glucose monitoring signals. Let's start with a little bit of background. Diabetes is a metabolic disease where the body struggles to regulate blood glucose levels. It's categorized as type 1 and type 2 diabetes, both involving issues with insulin but differing in their onset and progression. Women face higher risks of diabetes as they reach 65 and up because after menopause, they lose their potency to estradiol, the primary form of estrogen. This makes them more vulnerable to insulin resistance and diabetes. Because of hormonal differences, we really need to better understand how sex differences affect diabetes. The long-term goal of our project is to investigate hormonal fluctuations throughout a female's cycle to inform personalized, cycle-specific treatment options for diabetes.
For this project, we developed three goals. First, we wanted to identify the impacts of the menstrual cycle on CGM data, which has been understudied and never analyzed in a large longitudinal data set. In order to do that, we needed a method to classify the cyclicity of label-free glucose data. Finally, we wanted to analyze the combined effects of sex, age, and diabetes type on glucose signals. This project was split into two main components. The first was a case study involving 5 months of data from our group member Sarah's Oura Ring and Dexcom G7 CGM. Additionally, as a control, we compared Sarah's data to a male volunteer. Once we identified significant trends in the case study, we moved on to analyze a larger data set provided by Dexcom. We had a year worth of data for 16,000 diabetic individuals, split evenly between type 1 and type 2 diabetes. Additionally, this data is label-free for cyclicity. The only information we have is sex, age range, diabetes type, and the glucose levels provided by the Dexcom CGM.
From our case study, we identified clear cyclic patterns in my glucose data, as shown by the 32 to 33 day peak in the Loam-Scargill periodogram, which suggests a way to classify cyclicity just based on glucose data. Moving on to our larger data set, we found that a greater proportion of females in their 30s show high-powered 22 to 43 day glucose rhythms than any other group. Meanwhile, there are no high-powered monthly signals for individuals in their 60s.
Additionally, we found that across sex, individuals with type 2 diabetes are more variable in their Loam-Scargill power and periodicity than individuals with type 1 diabetes. So to summarize our findings, our results suggest avenues to create personalized diabetes treatment plans based on an individual's cyclicity status and diabetes type. And finally, we would like to thank our mentors for their assistance in this project. Thank you.